Hello, I welcome you to Explain Physics with Jesus Gazca. I introduce myself briefly. I am Jesus Gazca, I am in second year of high school, and my teacher is Ansel. Let's continue. Today, I will talk about two very important topics when it comes to talking about physics. They are also two topics that we said during our last physics class. The first one is free fall practice, and our second track is distance and direction. I will give a brief explanation on both topics before introducing ourselves to our presentation. What will I talk about today? Free fall, small introduction, examples given in class, distance and direction, small introduction, examples given in class, little video, and conclusion. Let's begin. Every body that falls freely has a vertical trajectory. The fall of bodies is an uniform acceleration movement. All bodies fall with the same acceleration, with kinetic energy in free fall. When an object loses height, it loses potential energy, but gains speed, and therefore kinetic energy at any point in the path. The sum of the kinetic energy has the same value or presentation previously do in class. This one. Here we do an experiment. I will give a little explanation of what we do in class. Material: 1 meter rail, 2 marbles of different size, a greater ruler, a marker, a stopwatch, 3 beaks or brooks. Here is the experiment. Okay. In the first experiment that we do, we have to drop the small marble from the top and off the rail and measure the time it takes to travel each 20 distant centimeters. Recorded and experimental data travel, the time elapsed for the marble to travel each of the marked distance, 20 centimeters, 40 centimeters, 60 centimeters, 80 centimeters, 100 centimeters. Then square each of data travels, test of elapsed time, and record the result in the data travel table. Here is the table. 0 is equal to 0, 20, 0.8, 0.64, 31.25, 40, 1.2, 1.44, 27.7, 60, 1.5, 2.25, 26.6, 80, 2, 2, and 20, 100, 3.7, 30, and 7.30. Okay, here we have to repeat the experiment again, but with a different angle. 0 is equal to 0, 20 is equal to 0.10, 0.31, 1000, 40, 1.4, 126, 68.4, 60, 1.7, 2.89, 20.76, 80, 2.2, 4.84, 60.52, 100, 3.8, 14.44, 6.92. And here again, we have to repeat, but placing the third peak and repeat step 3 and compare the table again. 0 is equal to 0. 20 is 0.5, 0.25, 80. 40 is equal to 1, 1 and 40. 60 is equal to 1.3, 1.69, 35.50. 80 is equal to 1.8, 3.45, 5.29, 18.9. And here we have to add 3 photos of the experiment. Here is the one, here is the second one. Okay, here are some questions. What's the falling time of the small marble different for each one of the marked distance compared to the time that elapses for the large marble to travel this distance? Keep the same height of the inclined plane. The larger marble was faster. How does the falling time of the marbles vary as the inclination of the inclined plane? With the less inclination, it has the slower the marble travels. What will happen in the extreme case that the rail is placed in a vertical position? The marble will travel faster and it will have less time. Just in a straight line by joining the points on the graph of distance versus time squared. It's not a straight line because it has change on time and distance. In which case was the magnitude of the last elevation of the marble greater comparing the inclination of the inclining plane, and explain what it happens. The marble was faster when it had a greater inclination because it took less time to travel. Here again, some photo. Let's continue. Our second topic, distance and direction. Distance is a scalar measure because it's dependent of a direction. It is expressed with a number of and its corresponding unit, be it meters, kilometers, or any other. In contrast, the displacement is a vector quantity that depends on the direction. Now I will show you the presentation that I do for my class. Distance and direction. Here are some questions that are true or false. Direction is unimportant and distance is described in motion. True. Most foot races are measured in meters. True. Motion is generally defined as an increase in distance. False. Direction is the length of the route between 2 points. True. A vector is any quantity that has no units of measured. False. Motion is a vector when it includes only direction. False. You can measure distance with a metric ruler. True. Words that describe direction include east, up, and left. True. Here we have to read this one. Frame of reference. Assume that a school bus passes by as you stand on the sidewalk. It's obvious to you that the bus is moving. It is moving relative to you and the trees across the street. But what about the children inside the bus? They are moving relative to each other. If they look at the other children sitting near them, they will not appear to be moving. They will be able to tell that the bus is moving only by looking out the window and seeing you and the trees whizzing by. This example shows that how we perceive motion depends on our frame of reference. Frame of reference refers to something that is not moving with respect to an observer that can be used to detect motion. For the children on the bus, if they use other children riding the bus as their frame of reference, they do not appear to be moving. But if they use objects outside the bus as their frame of reference, they can tell that they are moving. Questions. Define frame of reference. How does a frame of reference help and observe motion? If you were standing on a sidewalk and saw a bus by, how could you tell that the bus is moving? What might be your frame of reference? Here are these ones. Circles the letter of the correct choice. If you were riding on a bus, which frame of reference will allow you to detect the motion? Trees outside the bus windows. Which units will most likely be used to measure the distance between two cities? Kilometers. To find the distance of a road that changes direction, you must add up all the distance traveled in different directions. When both distance and direction are considered, motion is a vector. To determine the distance between 2 points on a map, you can use a ruler and a compass. To explain how to get from a point A to point B, you must describe both the distance and the length. Motion is something that is not moving with respect to an object that can be used to detect motion. Vector, quantity that includes both size and direction. Position, location. Direction, change in position. Direction, line along which something moves. Distance, length of the route between 2 points. Meters, SE units for distance. The appreciation method depends on a person's frame of reference. A vector can be used to represent both the distance and direction of motion. A meter is used to represent a vector. Speed is one way to measure distance. Running events in a track and file are named for their vector. The way a vector arrow for motion represents position. The length of a vector arrow for motion represents direction. And this is my presentation. Let's continue. I will show you a small video so you can understand free fall.
Skydivers and wingsuit flyers may call what they do free falling, but as you may have noticed by now, in physics, words mean something a little more specific. So let's explore what free fall is all about in this segment of Physics in Motion. Free fall is what an object does when it is under the influence of only one force, gravity. We have to go way back in history to get a handle on why this matters, but we'll keep it short. For thousands of years, scientists thought that how fast something fell depended on how heavy it was. Seemed only logical. But in the 16th century, one of the all-time Science Hall of Fame geniuses, Galileo, had an idea. He suspected that all objects, regardless of their mass, fell at the same rate of acceleration. If he were to take two objects, one light and the other heavy, and drop them from a height, they would both hit the ground at the same time. This showed that acceleration is independent of mass. Let's go try this ourselves. So between this watermelon and this cantaloupe, which do you think will hit the ground first? Both hit at the same time. The watermelon made a bigger mess, but as far as acceleration goes, we verified Galileo's point. It even works on the moon. Take a look.
In my point of view, both issues are really important when talking about physics, since it is necessary to know how bodies fall in free fall. In addition to know the type of acceleration, the second topic is using meters, kilometer, in order to know how the distance used is. I thank you for paying attention to my video. See you in the next second installment. Bye.